All right, in this video we'll talk about alternating series. What is an alternating series? Well, I'm not sure exactly how to say it because an alternating series is just what it sounds like. A series that has terms that consistently alternate in sign. So maybe it's a plus and then minus forever all the way through the series. Maybe it's minus and then plus. If they alternate from one to the other and it's consistent, then that's what an alternating series is. Okay? All right, now so it's about all I could say about it to just tell you what it is. So now I show you. So let's see, could you tell or could you give reason why you think some of these are alternating or not? Okay? So let's look at this one. I guess one thing that we can do is, we can try to write out the terms and we can see how the math works out, and maybe that would generate the belief in us that it's alternating. Okay, so here's a series -1 to the n power times 1 over n from 1 to infinity. Okay, so what does that look like? First term is -1. Second term is positive 1/2. Right? Because that seems to make it alternate. I get -1 to the first power, -1 to the second power. You take -1 to an odd power, you get a negative answer. To an even power, you get positive. I'll get -1/3 from here. I get positive 1/4. And negative, it keeps going, right? How many terms do you need to write? So, I would think that we would believe that that's an alternating series. I wrote the first 4 terms. Does that really prove that they consistently alternate forever? Well, I guess, even though any sane person probably believes that, yes, that happens, like me writing this out doesn't prove it. So let's do this. Let's give like a formal, a reason that you can't argue with, all right? Here's what that formula is like, okay? It's -1 to the n, which we'll take for granted. Yes, that will consistently alternate forever. That aspect of this formula does that. But, like, what kind of number is the 1 over n? 1 over n from 1 to infinity. Guaranteed to be a positive number, okay? So, all that's going to look like is -1 to the n, which does consistently alternate, times something that's always the same sign. So that's how I want everybody to be able to justify if they think something is an alternating series, by looking at its formula that way. Okay. Now, all right, what about this one? Does that look different? Yeah, but what's the plus 1 do? You got -1 to the n versus -1 to the n plus 1. That's only going to shift the signs. And I guess with series, if you wonder how it's going to work out, you can always write out the first so many terms. And so the first term of this is -1 squared times 1 over 1. So that's 1. And then you're going to get -1/2 plus 1/3 minus 1/4, right? You get the idea. It will look like that. Yes, the terms will consistently alternate in sign from plus to minus forever. But I wrote the first 4 out. Does that prove it? No, that doesn't. That doesn't prove that pattern will continue. I guess what would prove it is that, this thing must alternate in sign. It must go plus minus, plus minus. But again, the 1 over n is guaranteed to be a positive number through the whole series. So that formula there, which calculates the terms, is something that will consistently alternate, that part, times something that's always the same sign. All right, always positive. So let's emphasize doing it that way, okay? That would be definitive, but this really isn't. You kind of see what's happening, but that's what's definitive proof that it alternates. Okay, now so you get the feeling that, okay, maybe if I see -1 to the n somehow, then it might be alternating. Okay, sure. But that's how you're going to really know. So what about these two? Like this one does not have that aspect, -1 to the n plus 1, or -1 to the n. It's missing that, but does that mean just because it doesn't have that aspect to it that it's not alternating? Let's do this. Sometimes when we do this kind of math, we try to find some pattern that explains to us what's happening. So I'll do that with this one. I'm going to write the terms out so that I can find a pattern. Okay, so first term, cosine pi over 1. That's -1. Second term, cosine 2 pi over 2. Cosine 2 pi, that's 1. Okay, so that's going to be +1/2. Third term, so cosine 3 pi over 3. Cosine 3 pi is coterminal with 180 degrees. If you want, cosine's -1, so I get -1/3. Okay. Well, I think I see how it's going to work. I can write more terms out, but it is going to be totally identical with that one. All right. So, okay, maybe this is what it said, but I keep writing it. It's cosine of n pi is going to have to alternate between -1 and 1. You're going to get an angle coterminal with 0 degrees, and then one with coterminal with 180. So yeah, you're going to get a minus, then a plus, then a minus as you count through. Okay, so it's, if we want to, we could say, well, it's going to work the same way as this one. And so is that an alternating series? Yeah, if it really just reduces to being that, then it is. Okay, so is it alternating? Yes. Why? Well, because I noticed that it's this way, and then we did our analysis of that formula and why we think it's alternating up there. Okay. All right. So here's another thing. You might say, if it has this, right, we would sort of think it's alternating. If it doesn't, I didn't see a -1 to the n or anything like that. Doesn't matter. I have to look at it, see what it is. But what if that was built into it? Like, would this thing being there guarantee that it's alternating? Well, okay, how about this? Remember I said, like, this sort of thing's definitive proof. If you got the -1 to the n, okay, that will consistently alternate in sign. It has to. We'll take that for granted. But will cosine of n, will that stay the same? Is that consistently positive, for example? Well, I mean, cosine of n is different than cosine n pi. You're going to get cosine pi, cosine 2 pi, 3 pi. Up there in that one, you're going to find that cosine n pi is going to be either this angle right here, 0, 2 pi, 4 pi, or this one out here, pi, 3 pi, 5 pi. Cosine of 0, 2 pi, that's 1. Cosine of pi, 3 pi, that's -1. But that's just n. So here's what this looks like. First term, -1 to the first power is -1 times cosine of 1 radian. 1 radian being about 57 degrees. Then what? -1 squared cosine 2. Okay, cosine 2 radians. All right. Do we know that part of it, the cosine n, is going to be consistent in its sign, and that this just makes it alternate? We don't know that. It's not like this one. We'll write it out. We'll do the math, and you'll see. If I do 3, -1 third power, -1, cosine 3 radians, plus, you see the pattern by now, cosine 4 radians. And I don't think that thing is going to be consistent. And so let's look at it. Here's the proof, okay? We can tell, like, with the first few terms that the cosine of n, as you go through it, is not in consistent sign. So I get, say I put my calculator in radians, I say cosine of 1 radian. That's quadrant 1 is 0.54. Okay, so we'll get about negative 0.54. What's cosine 2 radians? That's over in quadrant 2. So we get negative 0.416. Okay, so plus yeah, so that next term is negative. Negative, no, that's not alternating. Okay, just isn't. We try the next one. What's cosine 3 radians? Negative 0.9. So here I got subtraction of that. So that's going to be plus, you know, roughly 0.99. Cosine 4, also negative. So we're adding it. So we're going to get, okay, let's do one more. If I did that next term, I would get a negative sign here. Cosine 5 radians. Okay, cosine 5 radians is 0.2. Okay, so I'm subtracting it. So negative 0.2. All right, yeah, so that part of it is not always plus or not always minus. And so it causes the series to not consistently alternate in sign. Okay? Okay, so this is the one that we see here that's not alternating. I cannot say, or as you can see here, it's not true that that's negative 1 to the n power times something that is always plus or always minus. And that's why the signs jump around in what looks like an inconsistent way, even though it does have this. All right? All right, so here's what I want you to notice. Just because it has the negative 1 to the n, or doesn't prove one way or another if it's alternating. We'll have to look at it in deeper terms to figure out if it is or not. Okay, so that's the first thing to establish is, do you know when you're looking at an alternating series? Can you tell if it's right in front of you? Okay, so next thing, we'll need to explore if you have a series if the terms begin to become consistently smaller. Okay, so like take this completely generic series made by that formula. So it's a sum from 1 to infinity of negative n squared over 2 plus 50n plus 40. And is there a point where the terms of that series become consecutively smaller? Like one after the other, they're smaller and smaller and smaller. Now, there's another reason why we would consider such a question. I'm not concerned about it right now. I just, do you get the concept of the terms of that series might become smaller one after the other at some point? All right, so sure, you get the question. Now, how would you figure that out? Well, I guess, I'm going to peek over here. I took my calculator and I found some of the terms. And I just wanted to demonstrate that, 1289.5, then 1290, well, they're getting bigger. 1290, now they're getting smaller. Okay, so yeah, that kind of thing. Does that happen? How could we figure out if the series is like that? Well, so the way that we do that doesn't involve making some table and, taking forever to do it and relying on some luck to find the point where that happens. The way that we do it is if the derivative of this formula were negative across some region of the n, then the terms would be getting smaller within that interval. Okay, so that's how we'll answer. Now, so how would you do that? Well, let's start by finding the derivative. Derivative of this is negative n plus 50 plus 0. Okay, so there's your derivative of this formula that series is made from. And to figure out when it's negative, I should start by figuring out when it's 0, and then I know everywhere else it's either plus or minus. So, okay, so I'll solve this equation. This would be the derivative of that formula to be 0, and I get n is equal to 50 as a fairly easy solution for it. And here's what we're looking at. If we had a little number line right here, and here's n, whole numbers, And then here, up here, I'll put what the sign of the derivative is. Okay? What is the derivative? Negative n plus 50. Okay, I just want, how does that vary with n? When is it negative, in other words? I know that at 50, it's 0, and that everywhere else it must be plus or minus. So I can take like a test point out here, and I can figure out whether the derivative is uniformly plus or minus just with one test value. Okay, so take like this. So say you had, what's something over here, 51. Say you put that into the derivative. What would you get? Negative 51 plus 50 is negative 1. Guaranteed that that thing will be uniformly negative for anything bigger than 50. 49, what's that give you? 49, negative 49 plus 50 is 1. That's positive. Okay, so yeah, I can tell that the derivative of this is negative once you go past 50. And that means that once you go past the 50th term, the terms of the series will become consecutively smaller. Okay, now that's how you do it. Is that true though? Like, you know, seeing is believing. So here goes. 49th term of the series, 50th term of the series, it got bigger. 51st term, smaller. 52nd term, smaller. Yes, it's true. The terms of the series become consecutively smaller after the 50th term. That's just what this is saying. Okay? All right, so if we need to know if that happened, that's how we do it. The derivative being negative proves that the actual numbers you get are getting smaller. Okay. Now, so what's the reason for discussing that? Let's go back to the lesson, and in question 5, the question is, does that alternating series converge? Not something we've talked about yet. I mean, you know what it means if a series converges. That we've discussed, but you know, how do you know if an alternating series converges? That's alternating. We proved it before. We did that on another page. Okay, here's how you do it. Get used to this test because we'll use it all the time. All right. Here's the test. Here's what would prove an alternating series converges. If you can answer yes to all 3 of these questions. Okay, so first, do the terms of the series really consistently alternate? In other words, like, verify that, you know, whether you think so or not, verify that it really is an alternating series. Second thing, do the terms become consistently or consecutively smaller in absolute value? Okay, in other words, is the absolute value of any term more than the one that comes after it? Okay, what would prove that? Well, we just spent all this time doing it. That series, you know, do the terms, yeah, the derivative being negative proves that at some point the terms will be forever smaller and smaller. Okay, so here with an alternating series, the terms are sometimes plus, sometimes minus, but it's just the absolute value of the terms. Or is that getting smaller? If you take the derivative of the absolute value of this formula that gives you the terms, and it's negative, then that proves it. Okay, so you work that out somehow. Third thing is the limit as n goes to infinity equal to 0. You know, take that expression out at infinity. Does it go to 0 in absolute value? If you can answer yes to all 3 of those, then that means that the series converges. That's the alternating series test. Okay, all right. So let's go through and let's check each part and see if we can say yes to it, and then we'll know. All right, so for that series, do the terms of that series consistently alternate? Well, yeah, I think that's obvious because what was the proof? Like, what do we say was definitive about it? The fact that the terms of that series are found by -1 to the n times 1 over n, and 1 over n I guarantee will be a positive number all the way through. Okay? All right, so it's like that. That's what makes it alternate. So I'll like say check, pass the first part of the test. Second part of the test, do the terms become consecutively smaller? Okay. Well, you might say, well, why don't we write them out? And then we can see. We already did that. Is a half smaller than 1? Is a third smaller than a half? Is a fourth smaller than a third? It looks like they're getting smaller in consecutive order. But, I mean, the series goes forever. I mean, it's just because you check the first 4 doesn't prove that it always does that. All right. So, yes, you prove it by showing that the derivative of this is negative. All right, so find the derivative of the absolute value of negative 1 to the n times 1 over n. To make the work a little bit easier, is just what is the absolute value of that? Do you see that the absolute value of that is just going to be 1 over n? Because the only thing that might make this number negative is that negative 1 to the n power. You know, that's either going to be 1 or negative 1. So if you just drop that, I guarantee you that will be the absolute value of that number all the time. Okay? All right, so we'll find the, the derivative, which is negative 1 over n squared. Okay. So there's your derivative. Now, do you have reason to believe that this is in fact negative? Okay. What kind of number is negative 1 over n squared? It's negative 1 over a positive number. And what kind of sign does negative 1 over... Well, that's got to be negative. Okay. All right, so the fact that the derivative of this is always negative proves that the terms are getting consistently smaller and smaller right from the very beginning. Okay? All right. So we'll put a check mark. We'll say answer yes because of that. All right. Last thing, limit as n goes to infinity of this, is it 0 or not? If we can say yes, it passes all 3 parts of the test and prove that the series converges. So, well, again, with the absolute value, all right, that's what the alternating series test says, so I have it there. But to make that limit easier to do, you know, it's like, can you simplify this and just say what the absolute value is? We talked about it up there. The absolute value of negative 1 to the n times 1 over n is just 1 over n, which has an obvious limit of 0 as n goes to infinity. So check. Okay, so yes, it passed all 3 parts of the test. If we just put all the math aside, you can say, yes, the terms consistently alternate, they become consecutively smaller, and they go to 0. If an alternating series does those 3 things, it converges. Okay, so final answer, that series converges, and I guess what that means is the more of these terms I add together, the closer I get to something. That something is whatever the value is that the series converges to. Okay, so I'll try a few more like this. Here's one that I would take it, the math looks a little harder with the logarithm and all that. But anyway, okay, so this would be question 7 on the lesson. Series 1 to infinity, negative 1 to the n plus 1 times natural log of n over n. So I can prove that the series converges if I can answer yes to those same 3 questions as on the last problem. All right, so what would prove that it's alternating? Does the fact that this is there prove it? The negative 1 to the n plus 1? That does not. That's not proof that the terms will consistently alternate forever. I would need to say that that's negative 1 to the n plus 1 times something that was always consistent in sign. Okay? All right, now how would I do that? Let's see. N's always positive, right? And natural log of what? Is that always positive? Let's do like this. Let's look at the the graph of natural log of n, I'll make my case for you that yes, that is in fact always positive once you go past 1. Okay, so let's say here's n, here's natural log of n. The curve looks like this. It hits the x-axis at 1 and 0. So yes, if you have an input there bigger than 1, natural log of it will be positive. Okay, so that's all I need then. That breakdown right there is that we have negative 1 to the n plus 1 times something that will be a positive number over another positive number. That's definitive. Now you might say, well, the first term's 0. Okay, first term's 0. After that, they will look like this and they will alternate. So yes, there I gave you some justification, some definitive proof that it's an alternating series. Okay, next thing is any term bigger than the one that comes after it. Okay, what proves that? Does looking at them prove it? No. Does finding the derivative of the absolute value of this and showing that it's negative, does that prove it? Yeah, that would prove it. If you could show this derivative was negative at some point, then we know that eventually that the terms get consecutively smaller. Okay, so let's see. What's that would be hard to take the derivative of, but given that we're working with the absolute value, we can drop that negative 1 to the n plus 1. And all we're going to have is natural log of n over n. Okay, so what's the derivative of that? Well, there's a rule for this, like almost anything. The quotient rule. It's 1 over n times n minus natural log of n over n squared. There's the quotient rule, derivative of natural log of n over n. That's going to be 1 minus natural log of n over n squared. And I need to figure out or show somehow that is in fact negative. Well, I guess we could do like this. What's natural log of 1? 0. Okay. Is that going to prove it? 1 minus... No, we need to... Remember that last problem. I need to make some kind of table or something like that. So let's do this. Let's see. When is this 0? And then I'll use some test values to figure out where it's positive or negative. Okay. All right. So there's the derivative. Let's set it equal to 0. That's going to amount to this. That fraction will be 0 if the top is 0 and the bottom isn't. So 1 minus natural log of n is 0. That's going to say natural log of n is 1. Or that n is e to the first power, or e. Okay. So the derivative is 0 when n is e. So here's what we're looking at. I get n, and I get the derivative up here. I know when n is e, the derivative is 0. What if it's bigger? Okay. Well, so give me a number bigger than e as a test value into the derivative. And we'll see what we get. Okay. All right, so e is 2.7 or so. Let's try 3. So I'll do 1 minus natural log of 3. And that is in fact negative. And then what would you do? Divide by 9? Still negative. So here's what the chart looks like. The derivative is uniformly negative if n is bigger than 2.7. If you test the other side, you'll find plus, okay, within the domain at least. And so, yeah, it's like that proves it at least after the third term, because this is 2.7, and then as we count by whole numbers in the series, you get to the third term. After that point, the derivative of this being entirely negative means the terms are getting smaller. That's proof. Any term will be bigger than the next term, at least once you get to the third term. Like after that, yes, eventually they'll decrease one by one forever. All right, so what do we have? Yes, the terms alternate. Yes, they will eventually get consistently smaller. It passes the second part of the test. All right, all because of this. All right. Last, is that limit 0? Okay, we can answer yes, that third part, that proves it converges. So can we agree that this, with that original formula, is just going to be this limit? Okay. And I would like to say that that's 0 and it passes all 3 parts of the test. How do you do that limit? I guess this form is actually infinity over infinity. It's an indeterminate form. So we use L'Hopital's rule, and that would amount to this. Derivative of natural log of n is 1 over n. Derivative of n is 1. Now can you tell? That's indeterminate. L'Hopital's rule says this is valid. You can do the limit that way. As n goes to infinity, 1 over n goes to 0, and it's apparently over 1. So yeah, so it passes the third part. All right, it passes all 3 parts. The terms consistently alternate. Eventually, they get consecutively smaller, and the terms also go to 0. We can say yes to those 3 things. Then we can say that the series converges. Bottom line. If I were to get my calculator and compute the partial sums and add the terms together as long as I want to, I'll just find that every time I add that next term, I get a little closer to something, whatever the series converges to. All this does is prove that it converges to something. Okay? All right, now let's look at some that are a little bit different. So take 8 and 9 here, which are, if they look different, they turn out to be the same thing. So let's look at the test real quick. I know I wrote out the test in that other sheet, but here it is on the lesson. Prove the terms alternate, prove that the terms become consecutively smaller, prove they go to 0 in absolute value. But there's some fine print. What does it mean if it fails the test? Okay, actually, if it's just true that if it fails the third part, then it diverges. If it fails the second part, it can actually go either way. It could converge or diverge. So how about this? If we ever recognize that a series is alternating and it fails the third part, then that's definitive that it diverges, right? Just like it says here, right? So why do I bring that up? Obviously, because this one's that way, okay? So does this series converge? It looks like an alternating series, but there's that 3-part test, and I'm going to skip the first part. I'm going to skip the second part, and I'm just going to look at the third part because I think that it's n plus 1 over n is going to fail that part of the test. And if it fails that part, it doesn't matter about the first 2. That's what I just showed you in the lesson. Okay, so watch this. I want limit n goes to infinity, absolute value a sub n. What's the a sub n? Just a generic label for that formula. What's that going to be? Limit n goes to infinity. And if you did take the absolute value of that, you would just end up with this, which is 1, which is not 0. So it fails the third part, and because of that, we can say that it diverges. Okay. Does it matter? What happened? Well, it makes no difference. If it fails the third part, it doesn't make any difference about the first and the second part. So if we take a quick look at something and we think it's going to fail the third part, maybe we'll just do that, see if it's true, and then we'll have our answer. Okay? All right, what about this one? It looks like an alternating series also, but wouldn't it be that, I mean, 3 over 2, that's 1.5. I think the same thing would happen. I'm going to skip this one. I'm going to skip this one. And what is the limit as n goes to infinity of the absolute value of that? If you wanted to, if you thought it looked more consistent with the way the other problems were, you could write like that. Okay? Well, okay, so what's the absolute value? 3 over 2 to the n power. Okay? Well, we had a rule at some point, it was on the formula sheet, and it said something like if that number is bigger than 1 to the n power, as n goes to infinity, the limit is going to be infinity. Take a number bigger than 1, raise it to bigger powers, you get ultimately larger and larger answers with no ceiling. Okay? Is that 0 as far from 0 as you can get? Okay? Fails the third part, it diverges. Okay? Is there some other way we could have known that? I want to show you the test. I want to show you how we think about alternating series. So I showed it to you this way. Is there some other way? You know, we did learn other stuff, and if you learned it, you might not be able to avoid thinking about it, but this is also a geometric series where r is negative 3 over 2. We said a geometric series will only converge if r is between negative 1 and 1, and it's not. So, sure, that's another way you could see it if you wanted to. All right, so yeah, fails the third part, definitive that the series diverges. Okay. All right, so let's talk about something else. So say we have an alternating series. Okay, that's one that we've already looked at. And say we know it converges. How do we figure out what it converges to? It's hard to do that. The only series that we ever were able to calculate exactly what it converged to were geometric series and telescoping series. For everything else, it's real hard to do. But anyway, so say we know it converges. We don't know what. In our class, all we'll do is learn to estimate what that number is. So that series converges to something. Call it capital S, the sum. How do you estimate it? Well, so for alternating series and only alternating series, here are the principles that will tell us. Okay, now so I write it in abstract mathematical terms right here, but you know, I'll read it to you. I'll tell you how I understand these when I see them. This says the difference between the sum, you know, if you were to add forever and find out what you get for a series that converges, capital S, the difference between a sum and the partial sum is less than the absolute value of the first term you did not use in the partial sum. So that's like the sum of the series up to some definite point n, and that's the very next term, the term you left off when you stopped. It tells you how close the partial sum gets to the sum. That makes sense. Does the partial sum is close to the sum anyway? If it converges, isn't it true? The more terms you add, the closer to that you get. Yeah, that's if the series converges, that's what happens. But an alternating series, that's how close those two are. If you subtract them, you get less than this. The other thing, when alternating series, because the signs change, as you compute the partial sum, it turns out you're either too high or too low every time. You never quite get to S. The more terms you add, the closer you get, but you do that in a way of being, I'm too high, then I'm too low, then I'm too high, and I get closer the whole time, but I'm always off by being too high or too low. So here's the other principle. The sum minus the partial sum has the same sign as, again, the first term that you did not use. So I guess you could say everything about estimating the sum of a alternating series, everything you could know about it comes down to the first term you don't use in the partial sum. Okay, so I thought, why not do an experiment about that? So here's an alternating series, but it's also a geometric series. So like everything we know about those two types of series should be true. It converges to negative 1/3. S is A1 over 1 minus R for an alternating series. So I know if I add and add and add, I just get closer to negative 1/3 the whole time. I just thought I want to try these out, see if it's true. Okay, so here's the prediction. 1. I'm just gonna pick a number just for the sake of illustration. It should be true that S minus S2, the difference between the sum of that ultimately out at infinity and the sum of the first two terms, the difference between those should be less than or equal to the third term. Okay. In other words, an absolute value, S minus S2, the sum minus the second partial sum, will be less than, what is the third term of that? Negative 1 over 8. So 1 over 8 or 0.125. Yeah, that's how close these are. You can add the first two terms and you can add forever. And the difference between those two numbers is less than 0.125. Okay? All right, that's a prediction. That's what that thing up there says. Is it really true? Well, let's try it out. Okay. So I'm going to say, is it true? Do we have some way to verify that? I mean, that's the prediction. So what is the sum again? Sum is negative 1/3. And what's the sum of the first two terms? Well, let's find out. So first term, negative 1/2. Second term, positive 1/4. Okay, negative 0.25. So there you have it. There is the sum minus the second partial sum. Okay, prediction. That will be less than 0.125. Let's find out. So I got negative 1/3 minus negative 0.25. That's going to be plus 0.25. I press enter, and prediction, it's, what it's going to be, I don't know, but it's going to be less than 0.125. And I do that, I get 0.083 repeating, okay? And it's absolute value. But there's your number. Yeah, did that turn out to be true? Oh, I did the math, yeah. 0.083 bar is less than 0.125. The prediction did come true. All right, so that's, when I say that kind of thing and other questions, that's what I'm saying is going to happen. All right. Next thing is, what's this? That tells you if you're too high or too low. So let's see. Let's interpret that again. I'm going to use the second partial sum as my example, but it says S minus S2 will have the sign of the third term. Okay, so let's write like this. Has the sign of, what's the third term of that? Negative 1 over 8. Okay. All right. So in other words, S minus S2 is negative, I guess you could say. If S minus S2 has the sign of the third term, that's negative. That just means it's less than 0. And what's another way to say that would be S2 is bigger than S. The second partial sum is bigger than the sum. It's alternating. Like I said, you're going to be too high and then you're going to be too low. And you never exactly get S as you add and add and add. Too high, too low, too high, too low. All right, so there's my prediction. All right, I mean, this was the first prediction I made according to the test. Here's the second one. Is it true? Is the sum of the first two terms actually bigger than the ultimate sum? Okay, what was the sum of the first two terms? It was negative 0.25. Okay, what's bigger, negative 0.25 or negative 0.3 bar? Yeah, it is true, right? The second partial sum negative 0.25 is in fact more than negative 0.3, so on. Okay. All right. So there's both predictions that can be made, and then I wanted to verify that they're true. Now I want to do this one last thing, and I want you to have this image just stick in your mind, because all alternating series work this way. And this image, if you can grasp it right now, will help you remember this later. So here's what I'm saying. In that series, it converges to S. Okay? It converges to negative 1/3. Okay? Every alternating series that converges has to converge to something, and whatever that is. Just look at how the partial sums bounce on either side of that. What's the sum of the first term? Sum of the first term is negative 0.5, in fact. And that's like right here somewhere. Okay? So S1 is negative 0.5. And then what's the sum of the first two terms? Well, we did the math. It's negative 0.25. So it's a little bit, it's up here. Okay? So there's S2. And then, here's what happens. What's the third term of that? Third term of that is a negative number. If you're here, and to find the third partial sum, you've got to add that next term, and it's negative. That's going to have to take you lower, right? So I guarantee S3 is down here, and then S4 is up here. And, because the signs alternate, I take the first term, the next one's positive, I'm too high. The next one's negative, then I'm too low. Then the next one's positive, then I'm too high. And that's why the first unused term tells you whether you're too high or too low, basically. That's another way you could do it. Okay? All alternating series work like that. Okay? If you're too high in one partial sum, the next one's guaranteed to be too low. And then the next one's guaranteed to be too high. Okay. Now, I want to try this out in a problem that's on the lesson. So let's do this. Let's take but 11 and 12 go together in a way that allows us to illustrate this. So look at them. We have this series that I've talked about in other problems. It converges. We don't know exactly what it converges to. But here's how we'll begin to estimate it. It says, suppose we use the sum of the first 9 terms to estimate the sum. How close will we be? And then if we use the first 9 terms to estimate the sum, will we be too high or too low? Okay? All right. So my work for those will be here. So I get this series, and I'm wondering, S9 minus S. Is the prediction made about how close those are? Okay. Well, it's, how about this? As we learn this, maybe we'll keep this handy. That's how you can predict how close the sum and the partial sum are together. I realize I wrote it backwards there, but if you're taking the absolute value of it, the order you subtract doesn't matter. But the difference between these will just be less than the first term that you don't use. So, I guarantee that the difference between the sum of the first 9 terms and the sum forever is just going to be less than the absolute value of the 10th term, because the 10th term is the next term you left off when you calculate the sum of the first 9 terms. Okay, so here's the statement that I can make. S9 minus S is less than or equal to, what is the 10th term? Negative 1 to the 10th power times 1 over 10? That's just 1 over 10. That's just 0.1. Okay? All right, so there's the statement. Now, so we do that. I still want you to think about this. If somehow I could do all the math, I could verify it. If I took the time to find the sum of the first 9 terms, I know I would be that close to whatever the sum is. Okay, so next thing, in 12 is let's just say it like this. For that series up there, is S9 too high? You know, you might get this close to the sum, but is it too high, or is S9 less than this? Is it too low? Which one is it? It's got to be one or the other, because remember I did say that you're too low, then you're too high, then you're too low, and you're too high. And every time you add that next term, you get closer to whatever it converges to, but too high and too low. All right, so I know one of those has to be the truth. But again, let's use this. That will have the sign of this. So I know that S minus S9 will have the sign of a 10. The 10th term of this series is positive. So that means S minus S9 is a positive number. So that means it's like that. Translate that, turn it around. It says S is bigger than S9. And that says that the partial sum is too low. It's under it. All right? So let's say we could give our answer like this. We could say it's too low. It might be that close, but it's a little bit too low. Okay? All right. Now, I guess you're going to think, how are you going to do this? If I show you this, I guess it's not so hard to write it down for this example. But other than that, I mean, how would you think about this if you didn't have it right in front of you? Let me show you how I would do it. I wrote that down for you so you'd have it. But there's another way that we can reach this conclusion. There's another way that we know that the ninth partial sum is underneath the sum. It's too low. Here's how. I know that the more terms of that series I combine, the closer to S, the sum, I get. Okay? Now I'm thinking about the ninth partial sum, the sum of the first 9 terms. Well, so what's the 10th term? The 10th term is positive, right? So I think about it like this. S9 must be here because the 10th term is positive, and if you took something and you added a positive number to it, it would make it bigger. And so I know that the 10th partial sum is up here. How do you find the 11th partial sum? Well, you gotta add the 11th term. The 11th term of this series is what? It's negative. Negative 1 to the 11th power times 1 over 11. Negative number. What happens if you take something and you add a negative number? Well, it gets smaller. Okay, so alright, the 9th partial sum must be too low because the 10th term would take you up here, and then you'd be too high. Alright, so that's, I to be honest, would not remember it this way, even though that's what it might say in a book. It seems easier to think that that's how it must work if the signs of the terms do in fact alternate and would make the partial sums look like that in this case. That's how I would think about it. Okay, so let's try 1 or 2 more. Here's 14b, and it's got like a similar setup to the others at this point, where I have an alternating series, it converges. How do you know it converges? Like at this point, can you look at that and tell that yes, it's alternating? If it's 1 over n squared plus 3, yes, the terms get consecutively smaller and they go to 0. It passes all 3 parts of the test. Okay, so I hope you could look at this point, you can tell that it converges. But so say it converges to something that you don't know. How many terms are needed as a partial sum to approximate the sum with an error less than or equal to 0.002? Will that partial sum be too high or too low? So, okay, I got this, let's like orient our thinking somehow. I know that the first term I don't use, it tells me how close I get to the sum. All right. So how about this? Let's take this series and find out which term is that big or slightly smaller. Okay? Why? Well, because that'll tell me the term that's going to dictate the error or difference there. And then I'll say, well, I just need to take the partial sum up to that point. Okay, so I'll do this. Solving it. It's not so bad to solve, especially with a calculator. You get this. You get this. Okay? Whatever that is, I don't know. But we'll figure it out. That's how you at least solve it. That's the number you get. So I get 1 over 0.002 minus 3 square root. 22.29. So if you could have the 22.29th term, then that would get you here. Okay? That means that the 22nd term is a little bigger than that. And the 23rd term, sorry, 29, the 23rd term is a little smaller than that. How do I know that? Well, because the terms of that series are, in fact, getting consecutively smaller. So what we want is that A23, that's the very first term of the series that's going to be less than this. Okay? All right. That's what I'm saying. That's my prediction. And it'd be an easy prediction to check. So let's do this. The 23rd term will in fact be negative. The value of it, 1 over 23 squared plus 3, okay? And then I get 0.0006. Yeah, that's smaller than that desired number. If you want to, why not? Why not check the 22nd? It's not going to be smaller than this, but we can try it. So I'll do 1 over 22 squared plus 3. And it's 0.00205. Just barely bigger than that. So yeah, when I said we got here, and I said, well, the term that's going to finally dip below this is going to be the 23rd, not the 22nd term. So you imagine that, okay, the 23rd term tells me the error, S minus S22 is going to be less than that number. S minus S21 is going to be less than this one. But I would need to take the partial sum up to this point to guarantee that the margin of error is less than or equal to 0.002. All right, so let's do this. Give our answer this way. We want the sum of the first 22 terms. That's going to be the error term. What exactly, I know I said it. What's the justification for that? Well, S minus S22 will be less than or equal to 0.0006, okay? Which is the first partial sum that's going to put it below that. All right, so that's the partial sum as needed. Will S22 be too high or too low? Well, I'll do this in my abbreviated way. So S22, so is that under the sum or above it? What's the 23rd term? 23rd term is negative, right? So if you were at S22 and you added the next term, that would be a negative. It would take you down. That means you're too high right here. So second statement, is it too high or too low? S22 has got to be bigger than S. Okay? So that'll tell you the partial sum that will get you within the margin of error that you want. And this tells you that it's too high. Okay? All right, one last problem, which will take us through the whole lesson, is this one, 15a. And it says that, so I give you an alternating series. It specifically says in the question to use your calculator to find out which partial sum will estimate the sum with an error less than 3 times 10 to the minus 7. Okay? Okay, so that's what it says. Now, is that exactly like this one? Yeah, it sounds like that one. This series converges because it's an alternating series. The terms get smaller. They go to 0. It passes all 3 parts of the test. So is this one. Both of them ask you how many terms do you have to add to get within some desired margin of error to whatever the sum is. But it would be hard to algebraically solve that one. Like this one, I set it up. It's just algebra to figure out how far I need to go. With this one, that would be hard to do. So it says use a calculator. If you read the question, that's just what it says. So what I did was I thought, I'll make a table, and I got my calculator. I calculated every term. And I thought I'd look for the first one that's smaller than that. Okay? And that would be the error term. And then I want to take the partial sum up to that point. And it's guaranteed to get me closer than this to the actual sum. Okay. Oh, how do I know that? Well, it's all this. This one statement that looks so simple. That's what it says. The sum minus the partial sum is less than or equal to the first term you didn't use in the partial sum. So I want to find that term that I'm going to leave off and take the partial sum up to that point. So which term is the first term less than this? Not this one, not this one, not this one. There. 2.8 times 10 to the minus 7. Barely smaller than 3 times 10 to the minus. That's what we want. Okay. So I'll say, well, that term right there, that's the error term. That indicates how far I need to go. And then I could say, well, just take the partial sum up to this point. Okay, why? Well, because how close that partial sum gets you to whatever the actual sum is going to be less than that next term that you left off. And so this partial sum is going to get you closer than this to the sum. Well, that's within that margin of error. That's why I've tried to find that term. Tell you I want the partial sum up to that point. So that'd be what? What partial sum is that? 1, 2, 3, 4, 5. So that's S5. Okay? And then it says I think it says in the question to actually calculate the partial sum. So if I say I got all the numbers here and I add them together and I round it appropriately, it's about 0.540. Okay? So that's the partial sum you want. That, some of the first 5 terms, will be extremely close to the sum. Closer than that number. Okay?